So today we are going to talk about checksums and Java, mostly about Java. Well, who am I? My name is Dmitry Chuyko. I work at a company named Bellsoft. Bellsoft releases and supports Liberica. Liberica 10 is a TCK verified binary distribution of OpenJDK for Raspberry Pi, so you can download and use it. Please do it. And we see our main activity in ARM 64-bit port in OpenJDK. We do it with, of course, other community members like Linaro, Red Hat, and we also keep an eye on 32-bit port, ARM port. And Bellsoft is a company that formed of former Oracle employees, just like me. And previously in Oracle, as a member of performance team, I participated in Java 8 and Java 9 releases, particularly in AOT project. And well, today we are going to talk about more recent versions of Java. So who of you have ever heard of ARM-based servers? Yeah, okay, yeah. Who uses them? I do it daily. And basically it's not that hard because they are available for quite a long time, and it's not a problem to take and to buy some relatively cheap cloud access. And by the way, the servers we work with, they have a lots of hardware threads, which is cool. And the server from right, it's quite powerful machine. So we are going to talk about optimizations in OpenJDK, optimizations that we made as a contributors. And well, it's a long road to make something, to optimize something. And doing that, we spotted some, well, probably general pitfalls with checksums. My today's story will be about optimizing checksums in OpenJDK. And probably it can be useful for regular Java developers because we need to know how things work. We need to know what to do and what not to do. And, well, to pick something. So probably you all have that thing in your pocket. A card, probably a credit or debit card. And we all know that digits there, they mean something. The very special last digit, it has a special meaning of checking all other digits on that long number. So there is a dedicated algorithm called Luhn algorithm, when you can just calculate weighted sum of digits and check everything. So not that complex, right? By the way, if you need to implement the check, please use some library, like the library listed here. That's from Apache Commons. And there are other algorithms. So if you need algorithm of similar class or even, well, more broader class, like just doing check of some check digits with a string API, you can pick that and use it easily. So that's for humans. And humans, they make mistakes. We make mistakes. You can tell me your credit card number using your phone, and probably you will make some mistake, and I will check your last digit, and that's all. So human can check, human can calculate such a checksum. A computer, well, they make them behave like ourselves, but they are much more simple. They operate with two symbols, two digits, 0 and 1, and they can basically do the same thing. We can imagine a checksum with a single character, which is 0 or 1, and that will be a parity bit, right? We can add that bit of data or just reserve it in a word and put that information. Probably we can easily calculate it using SOR operation. That's only a single bit that checks parity. What it will tell us? It will tell us that, well, probably if single error happened, some wire melted down, something happened, there is an error. We can waste more data for error detection. Like we can say, we'll have a check byte. And if we sum bits on each position in all bytes of some word, like the word listed here, we can then detect more problems. Like in some byte in that word, there was an error in that position. That may be useful. And again, if we will sum all that bits in that control byte, we'll get the very same parity bit. All right. So how to do it in Java? Well, it's fairly easy. We can take all the bytes and apply XOR operation based on some initial value of parity. And then, well, you can get parity bit value if you wish. It's also easy. You can just sum all to count number of bits in your control word or byte, and then to look at parity of the result. But there are some kinds of well, errors that are not detected by this approach, like transposition errors. Then you change the order of your bytes. You won't notice it in this control sum. So we saw some checksums. What they are? It is some data that's added to your message. Some, well, not garbage, but not the data that you are going to transmit, for example. And there are rules or functions to calculate that data, and they allow you to check the integrity of your message or your original data. But checksum is not something more complex, like it's not a hash function. You can use it as a hash function, but that's a bad idea, because checksums are designed to detect errors, so they are sensible to minor changes in your data. But the purpose of hash function is to make, well, quite different values from relatively close sources. And what's then the checksum benefit then? It should be much more easier to compute, like we saw the SOR example, right? It's a straightforward and simple function, can be implemented in hardware. Well, it's good. So again, it's not a secure hash, and you can use them for different purposes. Right? Some other notable types. If we waste some more space for storing our checksum, we can afford some nice effects. Like we can restore corrupted data. So those are error correction codes. So there are different kinds of codes. Okay. So let's look at some of, probably it's very simple and basic, but anyway. So we operate with ones and zeros, and we are going to talk about checksums of specific class, particularly circular redundancy checks. That are kind of linear code. They have very important property of that they are linear. So you can calculate parts of that checksums, and then calculate next part of it based on the previous result. And also, they are computed in a special way. When we represent our data as polynomials and calculate the remainder of their division. So the idea is, well, quite simple, right? If you have some number, like the number that we looked at before, we can write it down as ones and zeros. Those will be coefficients of polynomial members. So that's how number turns into polynomial. We also have a special polynomial that determines the CRC function. There are multiple, a bunch of them. Even for some particular length that they pick, there are variants, there are options. Like you see here, two popular options for length 33. Those are CRC32 and CRC32C, which stands for Castagnoli, for the offer. And they have a characteristical number, of course. So if you see that number, that means there is a polynomial, and you see the polynomial, there's a number. And the most simplest case is source sum, which is a particular case of CRC1, right? So we can calculate the same parity value based on just polynomial division. Okay, probably that's the most complex math here. Not too complex. Okay, so going back to Java, what do we have there? In Java, we have quite a simple interface for calculating checksums. So you can write your own implementation. And three standard checksums. There are implemented three algorithms, Adler32, CRC32, and CRC32C. Each has a corresponding class in Java util-zip package. And you can use any checksum implemented checksum interface for making a special filtering stream for input or output, which takes your some original stream and allows you to know checksum of that stream at any time. So that's easy. You see that a couple of methods were added in JDK9. Of course, they have default implementations in that interface. I just don't list it here. And the base method, of course, is the second one, which takes an array, some continuous data, takes two indexes, and then calculates the checksum of that part of data. And at some time, you can get from somewhere a smaller chunk of data, as small as int, and there's a method for that. But of course, all optimizations they target the method that works with continuous data, the chunks of data. The byte buffer API part, it also relies on this one. So it anyway goes to some code that has address in memory where is your data, and then just calculates checksum over it. So please use primarily this API. So you can easily turn array of any kind, like if you don't have array of bytes but array of longs, you can easily turn it to byte buffer and then pass to this function. So you can wrap it, and that will be more proper. So let's look at the checksums in started library. So Adler, that's one probably worth putting its code on the slide because I can do it. It's relatively short. And it exists for well, almost 30 years for now. Java has it from the very beginning, and the underlying implementation, so if you look into the class, you won't see any Java code like this from the right part of the slide. You will see just native methods, and the implementation will go to zlib library compiled on your platform. So that will be some optimized C code. But on different platforms, people need more, like on x86 or on ARM, and they do even more optimized implementation using so-called intrinsics. So what is intrinsic? Intrinsic is a special piece of code written in C or written in assembly that can be inserted instead of your method by a compiler. It can be done by C2 compiler, by C1 compiler, or even by interpreter, which is not a compiler, but it knows about some intrinsics. So people do this, and there are intrinsics for other. And two CRC checksums. You see the difference. The CRC32 was also there from the beginning, and it is, in this sense, very similar to other. It's also backed in the same fashion by C code, and by the way, it had, well, intrinsics not so long ago, written in macro assembly. And CRC32C was added in just in 9, and also at that time it was intrinsified for, well, multiple platforms. But there is a Java algorithm there also. So on platforms that don't have intrinsics, like for example ARM32, it works as a compiled code. Okay, so let's talk more about standard checksums. What means standard? Probably standard is something that you can meet anywhere. Okay, we saw that we can meet checksum in our pocket. That's not the only example. There are numerous ones. Like if I look into my laptop and I'm going to put some picture in my slides, I will probably take PNG image, and it will have other checksum in it. And then I'm going to send slides to someone else. I will zip them, and well, zip file will check and will contain CRC32 checksums. I store that file. Probably I have, well, RAID disks, so they can ensure that data integrity using source sums. And then I'll send it over the wire, over the network. Every packet that I send will have correction codes in its header. So, and even on my local file system, I have out-of-the-box command line tools to calculate checksums for files. That's fun, right? Okay, so that was for small data. And who knows some means or tools to work with big data? Just name any. Any buzzwords? Okay, that was just a guess. I can name you just two useful tools. You'll need widescreen and small font size. So yeah, buzzwords are like Hadoop or Cassandra or Kafka, right? And you surprisingly will meet the same checksums there. Like, then you compress sorted string tables in Cassandra, you will have checksums. Then you store database files in HBase, then you'll see checksums. And then you work with Hadoop, and more widely with everything derived from Hadoop, or anything that stores things to HDFS, you will face checksums. And every message in Kafka again. So probably too many of them, right? Too many checksums. What about, I don't know, calculating a checksum of checksums? Yeah? Makes sense? Sounds funny, but it does. Like, really, if you, for example, store your HBase H file, or so it's called, on HDFS, you will have both checksum in the upper layer and on HDFS itself. By the way, one of our goals when we performed our optimization was to look at what we can do with typical, well, Hadoop workloads or something similar. So Hadoop is interesting. Particularly, you can see an example of how HDFS works, how it uses checksums. Basically, what it does, you store some file. It is split into big data blocks. The default block size is 128 megabytes. And they are replicated across nodes. And along with each block on your local file system of any kind, of course, that's one more level, the special file is stored, which consists of checksums of chunks of this block. And the size of chunk is also a parameter. So it's 12 bytes. And you can specify the checksum algorithm. And the default has changed, by the way, in Hadoop across versions. And Hadoop has, well, its own means of calculating it, which went a long road of improvements and bug fixes. And if you open, well, bug tracker, issue tracker for any of the systems I listed before, and you will put like CRC32, for example, into search field, you will find a long list of improvements and bug fixes in that system, as well as in Java, by the way. So Hadoop is especially interesting. I mean here Hadoop-common, the core set of classes, because for checksums there are multiple implementations. And that also depends on the version that you use. For example, you can use a pure Java CRC implementation for CRC32 or CRC32C, written in just Java, plain Java. By the way, it probably doesn't take into account your Indianness. That's funny. It also can use that data checksum utility class. It can use classes from standard library, particularly CRC32. And there is also a special native library which contains those algorithms implemented in C with some mix of assembly code. And by the way, so probably you've heard of Hadoop. It's a Java system, right? You only need Java to run it. But that's not completely true. Because if you download the Hadoop distribution from the official site, you get native library inside it. And what platform this native library is built for? Some Intel. So what happens on ARM? It just doesn't work. You will use a native, you will use pure Java implementation, or you can build that library by your own, or you can set up using, well, some package system, and then you'll get that library. So those are big data, big systems, and we have hardware. So assume we set up Hadoop, run it on Java, and it will run on some machine. The architectures instruction set architecture battle is probably over, but still that families, they have interesting members. Like cryptic casts. Let's talk about them. On Intel, JVM works on x86. JVM knows what exact processor capabilities we have, so it's able to choose better algorithm implementation, and it does. So there are different branches depending on your hardware capabilities inside the implementation. There are special instructions and instruction sets like AVX, SSE, and different versions of them. So some nice instructions that are useful for speeding up CRC calculations are instructions that they do multiplication of polynomials. Of course, taking into account that we're working with zeros and ones. There's a bunch of them in SSE, in the special instruction set whose name I can't just spell. There is also a special speed-up instruction for CRC calculation, which calculates a part of CRC algorithm, one step, but it's actually a part of CRC32C calculation. There are also other instructions that may be useful in implementation. And what's for ARM? Surprisingly, well, ARM looks not the same, but somehow similar. It also has CMD instruction set, which is called Neon, and version 8.1 makes mandatory support for support of CRC instructions for doing step of algorithm calculating CRC32 or 32C. Again, surprisingly, the name is different, but the result is more or less the same. There is an instruction for polynomial multiplication, which is useful for their division. Other useful instructions, and a set of CRC instructions for different data lengths. Okay, so we have some hardware support. Probably we could do something with it. I'm going to tell you about our work with ARM. So, what did we get in OpenJDK? We had some machines to work with, and we already had some implementation, basically JDK9 code, and we decided to improve it because we spotted few potential places where we can do it. So to improve something, you need to measure it before and after. So I made some benchmarking using GMH benchmarking harness, and also some profiling. I will show it later. Okay, so if we speed up CRC32 or 32C calculation, how do we benchmark it? You've already seen the usage of main method in that class, right? That's not that easy, just make a simple call. So here you can see that it turned into a benchmark, which will, in the end, give us average time or speed. I've converted it to speed of CRC calculation. So let's look into results. We had the baseline version, which is in JDK9. If you download or build JDK9 for ARM, that will be the version that you will use for ARM 64-bit. That's a yellow line. And it was pretty good, right? You saw the options. there is hardware support in Neon instruction set. So there is an option to implement all the stuff using Neon. And there's an option to use plain arithmetic, right? Just implement the algorithm using basic commands. That's the lowest red line. So you see that Neon is much better than doing plain arithmetic, but the algorithm implementation we looked at as a baseline, it's really good. It's way better than calculating checksum using plain arithmetic. So you see how speed depends on block size. That's the plot. And one interesting peculiarity here is that the speed falls down when we worked with data larger than L1 data cache. So probably there's something that we can do with it, right? That's for one particular processor, which is ThunderX first generation. And surprisingly, ARM, as well as x86 instruction set, it has a special instruction that helps you to struggle with such problems. In many modern processors, there are special units that do memory prefetching. So they predict what memory you will be using soon, and they fetch that memory into caches to make it, well, accessible faster. But in some processors, there are no such units, or you can, for example, turn them off, like you can turn them off even in Intel processors. And in that particular ARM processor, there are no prefetching units, but it implements prefetching instruction, so you can do software prefetching. And we found optimal prefetching distance for such a benchmark and added prefetching to the code. So some results that we got. You see the baseline and also the improved version, and the speed is not falling down, right, on large data sizes. But, yeah, by the way, that's 2x sped up. That's cool. But for the very particular point of 0.5 kilobyte, which is actually a block size in Hadoop, and also a default block size, for example, in gzip, there is a regression in a few percent, which is really important for us. We can make it regress that in production. And the improvement that we see was so big only for one microarchitecture, which makes this change inappropriate. Okay, so maybe we'll just explore some other benchmark. Okay. Assume we have long file chunk, and we calculate the checksum of it using smaller pieces of this chunk, like 5 and 12 bytes, for example. Doesn't make sense? Maybe. Can we speed up this prefetching? This with prefetching? Yes. Like we can speed up it almost 3 times. But think about it. What happens in real systems? If you have a huge buffer, you have it. Why do you need some smaller chunks? You will just calculate the, for example, checksum of the entire buffer. You don't need that window. And if you need some smaller window, that means that you probably do copying. And in copying benchmark, there is no such a difference. And the main part is related to the benchmark we saw previously. So this benchmark was not appropriate, and prefetching change was also not appropriate. Wrong way. We are OpenJDK developers. We often walk wrong ways. So what we did, in fact, look into original code that you can find in JDK9. That's a piece of ARM assembly. It's really a nice handcrafted assembly code. I personally, like it a lot because it's very tiny, but it has few important optimizations. We noticed that it has one problem. It has a lot of data dependencies, so each next instruction depends on previous one. There are, it's a simple code. There are loads and CRC calculations using special instruction. So we just broke the data dependencies, did some code around it, and made usage of instruction level parallelism in the processors that we have. So processors have execution blocks, they have execution pipelines, and if you have independent instructions sitting together closely to each other, then they can actually execute in parallel. The interesting side effect here was that this code is more proof to underlying data, because in some processors, when you start calculating, for example, CRC checksum, not from the beginning of the array, but like from 4th byte, you're in trouble in terms of performance, because you immediately get performance hit because of unaligned access. So, what speedups did we get finally? That was 1.5x for the platform that we targeted at that time, but we also got speedups for other platforms. Speedup for newer Kevin platform is not that high, just because of it's fast. It's much faster, and it's an out-of-order processor. So it doesn't suffer that much from data dependencies because it can, execute a lot more ahead. So those were improvements. We measured them, we committed them, and you can get them in JDK10. JDK10 is released, and if you download or build your ARM 64-bit JDK, you'll get that improvements. But generally speaking, the intrinsics that we improved, for CRC32C particularly, that intrinsic was used only in C2 compiler, and as you remember, I mentioned that there is another compiler, C1, and there is interpreter, and imagine that you receive some data, like over the network. And those are important data to receive. Probably you can process them slow, that bytes, but you wish to receive them. So your code that checks, like for example, CRC32 checksum of that bytes, it should work fast from the very beginning. So we made that improvement for CRC32C checksum. It now works both in C1 and interpreter in ARM 64-bit. And that makes your code much faster. If you calculate a lot of checksums in interpreter on C1 or on C1, well, you're lucky. It's faster now. But C1, C2, interpreter, what's missing here? Are C1 and C2 the only compilers we have nowadays? Who knows something else? Yeah, right, Growl. And surprisingly, Growl is under the hood. You can get it out of the box, then you download at least your JDK for Intel. But it's not the only platform that's targeted by Growl. And Growl doesn't know about, well, some code in hotspot that implements something. No. You need to teach Graal to use, for example, your intrinsics. And it's called a substitution for some method. So we made it for CRC32C. And it also gives a nice speed up, as you can see. And probably it will be interesting for you. AUT is implemented for AArch64, for 64-bit ARM. And it's already in there in mainline. And along that AUT implementation, there's a new Graal import. So you can enable Graal on JDK11 on ARM servers, and you will have that improvement there. That's cool, I think. Okay, so we talked about Hadoop a bit, right? So what happens there? Will Hadoop benefit of that change? Actually, no. If we haven't implemented something, Hadoop works on and compiles on JDK 8 and above, and the original code in Hadoop free branch was working only with CRC32 library implementation. And so if you have pure Java on Hadoop.free.0.0, it can work effectively without native library if you switch your checksum to CRC32, but it will work slowly if you set it to CRC32C. And we made it work faster if you run on JDK 9 or above, where we have intrinsified effective library implementation. So that's the kind of code that dynamically detects your Java version and then makes proper calls to library stuff using method handles. It's been released again this spring in Hadoop version 3.1, so you can get it. All right, we improved some things at ground level, at upper levels. How can we evaluate them? Well, we can. We made some Hadoop setup. Probably, I don't know, we are among few people who actually run latest version of Hadoop or some other systems on ARM servers using, well, not yet released Java. That's fun. If you're interested, ask me. And so we built up some setup of Hadoop 3.x. That was, 3.1 snapshot. And we haven't improved native library, so we excluded it. And made a pseudo-distributed yarn, well, single node cluster. That's a configuration not intended for using in benchmarks, but we are going to evaluate single change, not to estimate the overall performance of some cluster. And we took some popular harness to do runs. The question was, are we able to detect the influence of such single point change in some big workflow? We were going to look at profiles to see the exact methods that we have changed. So we have an option to, well, you have many options for profiling on ARM servers. And we fixed support for the platform in numerous. But they preferred a async profiler that's a kind of precise and low overhead tool written by Dmitry Chuyko. We also fixed platform support there. And then they used CPU flame graphs produced by that async profiler using latest hotspot with our changes and Hadoop before and after our changes. So, for example, we took a Terasort workload, which probably not so dependent on CRC calculation, but still, we wondered if we'll see something there. Okay, data CPU flying grass there. If you're interested, please ask me later what does it mean. And but basically, they measure CPU time spent in all the methods that were sampled. You can find anything here, right? But hopefully, there is search and there is zoom. So we can look precisely on map and reduce parts of this flame graph. And we actually see, I don't know if you see it well, but we can spot the original and the new version of the code in that profiles. And the number of samples decreased like 9 or so times. And spotted CPU time also decreased. That predicts us 1% improvement in non-profiled configuration, but actually it was more. It was like 5%. Not bad. For a big workload to make 5% improvement with a single change, well, 2 changes, that's good. So maybe there's something in the middle that we can examine. Yeah. There's a special benchmark in Hadoop-common itself, and we used it to compete and to compare the native library implementation. So I took a few different machines here, for example. First one is Intel machine with AVX2 support and SSE 4.2. So you can see the results dependent on the count of threads. There are also different parts of long result table with different sizes of block. But we'll look at more important one with half a kilobyte size. So we can see here that, first of all, that was the right decision for Hadoop to pick CRC32C as a default checksum with a native library implementation. You see in the rightmost top corner the number that is calculation speed, so higher is better again. And it's, well, way higher than anything else. It's the fastest one. Why it happens? Because Hadoop native library uses bulk approach, which works very well on out-of-order architectures, where we calculate few independent checksums for few blocks. So we have independent instructions that can execute in parallel in hardware. And native library implementations takes that into account. And also we can see that, yeah, they made a great improvement, more than 2x. And yeah, on Intel also. So next one is KVM ThunderX. Here we beaten up all implementations with our Java implementation, and particularly pure Java by like 4x, which is great. But still, if you don't have any options, use native library implementation, it's good enough. And on T99, again, we made a great speed up, all the 4 times. But still, it's preferable to use native library. Okay, maybe too much and too many CRC checksums, right? Yeah, so let's go to conclusions. Just a few words here. So please, if you have any kind of problem that requires data integrity checks or something like this, analyze it. Probably you will need checksums. Maybe you will need some other codes. Please choose carefully. Maybe you will need hash codes, maybe you will need secure hash functions. Maybe you will need error correction codes, like read Solomon codes or something. Then prove your choice. Well, make evaluation, run benchmarks, look into implementations, pick your options, like pick your size of your blocks if you calculate CRC checksums. Pick your hardware. And if you use some algorithm, please look at standard implementations. They are optimized. They are tested. Like if you need some checksum, well, take CRC32C. Use Java implementation. It will work just as you expect, fast and correct. If you need something else, please look into libraries that are widely used and well tested, like Apache Commons. And then, after some time, you will have to re-evaluate your choice because things change. Java is improved, libraries are improved, and platforms are also improved. So, and hardware, of course, and you have to do it. So please keep your powder dry and check your checksums. Thank you.